All right, let's just pick up where we left off yesterday. Uh, Obviously, if this is a complete review of National Electric Code and we're only in section 225, we're going to be picking up the pace a bit. And, some of this is just putting the code, or at least sections of it, up on screen so that we can get an understanding of its format, layout, and structure. We have a lot to do. So let's go ahead and dive in. Section 225.37, identification, where a building or structure has any combination of feeders, a permanent plaque should be installed at each disconnect, denoting the location of all services and feeders. And in solar, one thing that can really get you hung up on inspection is keeping track of all the labels and warnings and stickers that you need to put at each location. And it's called out in section 690, so there's repetitive content. So you can be flipping back and forth through 690, getting your list of stickers, and there's updates to the information that are on these stickers. The safety standards in solar changed so much that one update in 2017 is you have to tell the on-site inspector which code you are meeting for rapid shutdown, because the rapid shutdown requirements for 2014 give you a little bit more wiggle room than in 2017. Not a huge deal, but the main thing was there's a larger perimeter in past versions of code where you can have live conductors, and now it's like a 1 foot perimeter around the array. You actually have to put that on a plaque by that disconnect that's accessible, readily accessible for the utility to power down the system if they need to. And that's not just a solar requirement. What we see here in a more general basis is a requirement for when you have any combination of feeders feeding a building, there should be a plaque that tells the power company the location of those feeders. And so, we're used to having our utility feeder circuit. Well, now we also have a solar circuit that's a feeder circuit. So, supplying information at a readily accessible disconnect is a good thing, and we need to work with our utilities and fire departments to make on-site solar power something that they don't need to be so afraid of. This is kind of interesting. You'll find disconnect switches that are remote operated. An automatic transfer switch is a remote operated disconnect switch. But also now they're expensive. They're about $100, but you can get motor controlled circuit breakers that will manually open themselves or close themselves based off a computer program, like a smart home application. So you might ask yourself, well, if I have to buy a disconnect switch and my choice is I have to buy a knife switch disconnect per the utility, maybe I can get ahead in the permitting process by calling the inspector, calling the permitting office and saying, look, the knife switch disconnect is not a part of National Electric Code. It's a jurisdictional requirement. And what we want to do instead of putting a knife switch disconnect is install an energy distribution panel, and it's going to have switches for all of these things, and even an automatic transfer switch that isolates the home when the power goes out. So do we have to spend additional money on a knife switch disconnect that really doesn't have any role other than to insert a failure point into the system because we're already compliant in so many other ways? So what constitutes a disconnect switch? And mainly the thing to know that if they're power operable, they also need to be operated manually in order to qualify as that main disconnect switch. So a main disconnect switch, it needs to be field operable by an on-site person. Just having it automatically open on a control circuit does not constitute as your main disconnect. You know, some of these others, let's see, there are some minimum disconnect ratings. You know, this is the one that I think is important, is for a single family home. You know, we have this requirement for a minimum service of 100 amps. So if you want to get into, say, tiny home construction, and you're wondering, well, what size service panel do I need? Obviously, 200 amps for a huge home. That's, you know, what about for a tiny home? You know, you need to be putting in a 100 amp service panel for a dwelling unit. Then we get into rules for circuits that are over 600 volts. So you may be getting into ground-mounted solar design, where you get into higher voltage systems, and sometimes in higher voltage systems, protection requirements drop out, and that's usually because there's additional protection requirements elsewhere in code that are making for up for that simplicity whenever there is simplifying for going into higher voltage. You know, there's this kind of myth that a behind the fence project doesn't have to follow code because the utility guys are doing their own thing and not enforcing all these harder regulations onto your projects, but not necessarily following themselves. You know, there's so many more when you get into specialty system warning labels and protections. Anyway, we'll get to it. Let's see. Up is generally indicated with being on, and down is off. And sometimes it's hard to remember that, you know, what direction is supposed to be on. Just imagine that you're being zapped with electricity and your arms are flailing up in the air, and so your arms are up, and that's on. And then when the electricity current that's electrocuting your body gets taken away, your arms fail down on the ground, and that's off. You know, up is on, down is off. That also applies on a panel board. You know, up is down, up is on, down is off. You know, what this is visually indicating. You know, if the switch is side to side, you know, right on, left off, that's not considered indicating. So switches need to be in kind of vertical positions where they're visually indicating, with up being on and down being off. Substations, you know, here we have requirements for, you know, not just a plaque indicating where feeders are coming into the building, but a plaque that says you have to have a permanent single line diagram of the substation that lets someone know where they're going on. And this is just an example of, you know, if you're in a behind the fence over 600 volt project, you know, there may actually be more requirements for you rather than less requirements to abide by. You know, not just putting a directory of where the power is coming in and out of the building, but also a simplified electrical diagram that can tell the inspector what's going on. You know, a good electrical inspector who knows their stuff should be able to inspect your system and not know anything about solar, but based off a simplified one-line diagram, look at what's going on and be able to identify any obvious safety concerns like wire ratings not being considered or temperature issues not being considered, stuff like that. So we talked about number of services. Generally, you try to supply one service to the building until you get into higher power draws, but there are a lot of, or you have standby systems, solar arrays, on-site power. You're not supposed to supply one building through the interior of another building, and so it's, well, what's considered the interior of a building? You know, we have you know, basically, if you put enough dirt between two buildings, you know, if you encase your wires in enclosed concrete, that's considered not being inside the building. Let's see. So other conductors for services are not allowed in the same raceway or cable. And where we see this pick up later on in code is you get into your solar cables and you say, well, am I allowed to, I have AC solar and then I have DC solar, and they're both, you know, you have the DC side plugged into the inverter, the AC side plugged into the inverter. And you might ask yourself, well, is DC and AC allowed to share the same cable? Or you might have your solar inverters and then a wall display next to it, and you want to run power to a service panel, and you might say, well, am I able to put in you know, regular circuits, load circuits, in the same raceway as my solar circuit? And there is a section later on in code that says for solar cables, you're not allowed to combine your load circuits with your solar circuits. But we also see that reflected, you know, early on in 230 services, where, you know, for our service entrance conductors, you know, for our supply, other conductors are not allowed in the same raceway or cable except for grounding conductors and bonding conductors and other conductors having to do with on-site energy management. And they're not just saying supply, it says load management control. So what we talk about is maybe that involves not just decreasing your energy usage, but increasing your energy usage in a cost-effective manner. You know, if you want to install a Bitcoin miner right next to your solar array, you could call that a load management control device and use the same conductors. And then we see our raceway seal requirement that we've already talked about yesterday. Clearance requirements, you know, again, we saw clearance requirements for feeder conductors, and it's almost like, am I having deja vu? Because yesterday, I know we got into, well, yesterday we were talking about feeders, and today we're talking about services, and services are a type of feeder. And so, you know, some requirements that were for feeder conductors, you know, they're just trickling them down into services and then maybe expanding. Now, what's the difference between a service and a feeder? Probably, you know, in the past, we've had feeders that are not just our utility service, but power standby systems, generators. Now we're getting in with solar leasing. We're getting into solar as a service, as a second service on the location. And, you know, again, we have to stay 3 feet away from open windows, doors, similar locations on the outside of the building, except up at the top of the building where you're allowed to sneak alongside the dormer. So you could actually be dinged on an inspection if you're doing an exterior conduit run and you're saying, well, I'm doing an exterior conduit run so it's safer and it's also easier and cheaper. I'm not a fan of exterior conduit runs. I like doing interior conduit runs. I think they look a lot better, and I think those aesthetic values are very important. But a lot of installers will just stick to the outside of the building for a variety of reasons. When you're running that conduit down the side of a building, you have to stay 3 feet away from windows and doors and human, you know, the ability for a human to open up a window and stick their, you know, wave at the parade that's going by the window. You know, you don't want them to get in contact with that line. Let's see. So now we have a call out that says if we're using on a service a grounded conductor, it's allowed to be uninsulated. And so in solar, when we get into our equipment ground conductor or even our grounding electrode conductor, there will be a call out that says you are allowed to use bare copper wire. You know, like yesterday we were talking about how you could have a DC grounding electrode conductor and that you're allowed to connect it to the AC side of the system. And there's a couple of different ways you can do that. And one way is to connect it to the AC equipment ground conductor. And so you could have an insulated equipment ground conductor running up to your rooftop that's grounding all your metal AC parts. Maybe you have micro inverters up on the rooftop, and you still have to ground your racking, and your racking is exposed to DC electricity rather than AC electricity. Well, let's not worry about those nuances. What it says is you can connect the DC side to the AC side, and there's a bunch of rules for that. Another rule is you can just take bare number 6 copper up to the rooftop as your DC grounding electrode conductor and connect it right onto your ground rod at the bottom of your house. And that also might be where the AC side connects to. Your DC and your AC grounding system are touching at that point. Where you touch them together doesn't really matter. They have to be grounded. And this is saying, well, you can use uninsulated conductors if they are grounded conductors. If they are connected to ground, they can be uninsulated for a service conductor. And we see that, you might see that you're doing a solar design and you're used to running bare number 6 copper up to the rooftop, and all of a sudden you use a different designer and they're saying, no, you got to have a green insulated conductor and we're running it inside the building. Both are acceptable methods. There are requirements that say not smaller than number 8 in general. Then there are requirements for protection against physical damage. And one thing that's kind of interesting is in solar, that bare number 6 copper that runs up to the roof, code says it shouldn't be smaller than number 8, but it has to be number 6 if it's going to be bare and run up to the rooftop. And that's because, you want it needs to be a little bit more robust than number 8 if it is going to be bare. So we see one rule saying it's allowed to be bare, another rule saying not smaller than number 8. But then in solar, you get into a specific rule that says if you're going to run bare copper up to the rooftop as your equipment ground, you got to uptick it one size and make it a little bit more robust than number 8. Then we get into spliced conductors. This protection against damage requirement is something that comes up a lot when you're connecting your grounded conductor, your grounding electrode conductor to your ground rod. You get a little clamp that clamps the bare copper onto your bare copper ground rod. That needs to be protected against damage. We're getting into conductor splicing, and splicing is when you take one conductor and you're out of length on your conductor, and then the conductor is supposed to pick up, and you install a little junction box and you splice them on to each other. So you're allowed to splice conductors in most cases, or it says tapped. Tapping is where you might have one line and you want to install another line, and you connect them all up inside a junction box, and that would be a tap rather than a splice. It says you can have spliced conductors in accordance with certain rules, and these are rules that apply to Section 300 wiring, so we'll see those rules pop up. You're supposed to have one set of service conductors unless you are not using one main disconnect and you have up to 6 disconnects in separate enclosures that are grouped at the same location. So if you're just doing a main lug only panel, that might not be, the disconnecting means might not be in a separate enclosure, but this might be if you have a service and it's running out to 6 separate fuse disconnect switches. You have one set of service you could have 6 sets coming off of that transformer if you wanted to. Or buildings with more than one occupancy. I mean, it's pretty lenient. you can have additional service entrance conductor sets for your standby systems and solar systems, and that might be if you want to have a battery up at your transformer that provides power during a blackout to everyone along the distribution circuit. You can run a new service entrance conductor set for that. So one thing to think about on that 6 disconnect switch rule, it's really not a hard fast, you can only have 6 switches at this location. It's more of a, you can only have up to 6 switches for this specific type of use. So for your main service, you can have up to 6 disconnects with 6 service entrance conductors. For your backup power supplies, you can have up to 6 disconnects with your 6 service entrance conductors. And you know, maybe there might be even additional situations where, you know, you can, you know, if your jurisdiction allows you to have load management devices being different than emergency backup devices, you could have, you know, 18 disconnect switches, although most jurisdictions would say that would be a pretty messy design. Service entrance conductors are sized for 125% of the continuous and 100% of the non-continuous loads. You know, that's just a general sizing principle when you're looking at your ampacity of your continuous loads. You add 25%. Your non-continuous loads may be sized for less than that. You know, in solar, they'll go in and they'll say on the DC side, when you're not controlling the power with like a DC optimizer, you know, you size for 125% of the amperage output of that panel, but even before you get to that point, you have to throw on an additional 25%. And a lot of solar guys is like, that's weird, that doesn't show up in any other part of code. And the reasoning behind it is that your solar panel, the spec sheet is done at standard test condition, and that's not very indicative of actual field performance. So in the solar industry, you know, with your DC output circuits, you're sizing not just for 125% of the continuous load, but there have been additional correction factors applied to that, and that's simply because it's a different special device where the listings are really messed up, and that it doesn't really, you know, the standard test condition for a solar module is what you would expect on like a 45-degree Fahrenheit day with no humidity in the air and the sun facing directly at the panel. It's just not, you know, when you go into Home Depot and you buy a backup generator and it says it's 12 kilowatts, you know what you're buying because of a variety of reasons. Solar, you know, they might have to have some additional sizing principles because the sizing process is more nuanced. Let's see, then we get into minimum ampacity, where it just says, even if you're doing a service that has a 2-volt, you're just trying to power a USB thumb drive. Like I don't, very low voltage appliances, there are minimum ampacities for your conductors to consider as well. For systems under, grounded systems under 1,000 volts. So we'll see some of these minimum requirements show up on our charts a little bit later in the program. We see in 230, we see a main bonding jumper shall connect the neutral to each service disconnecting means enclosure. Yeah, this is where your neutral is being bonded to your system ground. If your service disconnecting means enclosure is connected to your grounding system and your neutral is being bonded to that grounding system, there's actually one point in your system where you're taking your neutral wire and taking a piece of metal and touching it to ground and leaving it like that. Now, normally you wouldn't want to take an energized wire and and a paper clip and touch it to the unenergized wire. When you have a energized wire at higher voltage and a grounded wire at 0 voltage, and you touch them, you know, you're pushing that boulder off the top of the mountain, and it's rolling down to its lower voltage potential. You know, this is kind of like the drain on your system that gets all of the extra electricity, like if you're ground faulting, to actually flow into your system ground rather than remain energized. You know, if you're ground faulting, you want that electricity to drain into the ground. You don't want that metal case to have high voltage on it, and then someone goes and touches it, and if they're connected, if they have enough you know, low enough resistance, they're now the ground path. We want to avoid that. We want to have a effective ground path that connects these metal devices to ground. And at one point in the system, the neutral is connected to ground as well, and that provides a reference, so that if you're monitoring your neutral wire and you have a reference point to ground, so that you can compare the voltage in the neutral to ground to determine if there's a ground fault, to enable your ground fault detection systems. But it only occurs at one spot. Now, if you're grounding the neutral and you're connecting it to ground at multiple spots across your system, then you're eliminating that reference point. Your ground fault detection circuits have a blind spot in them. That's where the, you know, inspectors looking at the ground fault protection systems of inverters and seeing that they're grounded, and, you know, are saying, well, isn't that going to create a blind spot if there is a ground fault? And that's burnt a few buildings down on your older style central inverters. It's since been inverters have been updating their ground fault protection systems ever since. Okay, so listing is a common requirement that can get confusing. You're required on job sites to use listed parts, and the most important thing about a listed part is that it's listed for a specific purpose, so that the listing states that it meets standards required for a certain purpose, or that the device has been tested for a specific purpose. Sometimes the need for the device comes out before a standard can be written for it. And so you might have you know, a device that says it needs to be listed for a rapid shutdown standard. Sometimes the rapid shutdown products can come out before the standard is fully finished. The most important thing to think about is on this, when you're using a product, it needs to be intended for its use. And when you're thinking about, can I just go to Home Depot and pick out any wire and wire it up to my solar array? You know, the answer is you can, as long as that cable is listed for use. You know, if it's listed for a high temperature, environmentally resistant, direct sunlight exposure, you know, in a wet environment, then yeah, you can use that cable up on the rooftop. So the important, but if you're, you know, the common one is you might get a splice kit. And what I'm thinking about is there's a splice kit that you can commonly find at Home Depot that is a shrink wrap tubing, and then there's a terminal block inside the shrink wrap tubing with a little screw on it and another screw on it and a bus bar connecting the two. And so you go and you put in your cables on both ends, and then you take a heat gun like an air dryer and you shrink the shrink tube, and now you have an inline splice. And that is intended for direct burial cabling, or even in kind of like underground deep sea welding operations. But it doesn't necessarily mean that it's listed to go for your microinverter branch circuits up on a rooftop. It may not have the same physical protection requirements for that. So if you're borrowing things from a different components from a different industry because you think that it's a better solution, that's when you really need to go and read the listings to make sure that you're not borrowing something from the direct burial industry and then trying to use it on a raceway up on a rooftop. Let's see, wiring methods for 600 volts or less. We have flexible metal conduit, not over 6 feet long, or a different kind of metal conduit called liquid tight metal conduit. Flex metal is exposed metal. Liquid tight has a PVC coating over the top of it, not over 6 feet long between raceways or raceways and service equipment. And so we were doing one job where we're using flex conduit to come into the rooftop through the roof cap. The only way we can make that conduit bend work in an easy manner is to take flex conduit up on the rooftop and then route it through the roof cap. It's harder than it sounds. We had to use a 45-degree fitting just to get the conduit going in the right direction. Like a metal flex conduit is still made out of metal, and so it's still going to have a similar, if not wider, bending radius than like EMT conduit, because you don't get additional flexibility in your aluminum than you would in that aluminum that you have to flex by hand with a conduit bender. It's still the same, but it's just easier to field manage in the field. You don't have to get up on the roof and do a customized conduit bend for your specific purpose. So this flex conduit run should be not more than 6 feet long. Normally you wouldn't have a flex conduit run that's longer than 6 feet because flex conduit is very expensive compared to non-flex conduit. I mean, it's like 5 times as much. So you get into doing 30-foot, 40-foot flex conduit runs, and your project manager is going to yell at you because it's a waste of money. That said, we had a design where we're going in through the roof cap with flex conduit, and the inverter room is located directly below. And so the client says, well, we had called for putting a box right below the rooftop for the flex conduit to land into, at which point we would transition to EMT and dry rated wires. And the client said, well, I'm doing this as a self-install. I'd rather spend more money on material and less money on figuring out what to do. And so can't we just run these flex conduit runs directly down into our battery room? That was about 10 feet difference between the roof deck and the battery room. And your flex conduit run should be not over 6 feet long for your service entrance conductors. So, technically, no, that would be a code violation. Cable tray systems. So we get into cable trays to support larger service entrance conductors. But then there are specific cables that can only go inside these cable trays. And we also have a MC cable referenced here, as we'll learn later. That's called a metal clad conductor. And so just now, since we're on the same slide, one solution, if you wanted to use a flex metal conduit and just run it from the rooftop all the way down to the battery room, is to throw out the metal conduit aspect of it. We'll learn that DC wiring has to be enclosed in a metal raceway, but metal clad cable counts as a metal full enclosure, and you could just run metal clad cable straight from the roof penetration down to the battery room. So this is more just saying flex metal conduit is not a really good thing to use over 6 feet long. There's a reason why this rule is in code, and it's a safety reason, and we could go and research it and find out what that safety reason is, or we can take them at their word and just say, for some reason, we shouldn't use flex conduit that's more than 6 feet long, and it's a more expensive way to do things anyway. And there's other solutions out there that are better solutions, such as metal cable, where you would have the runs being longer than 6 feet. Spliced conductors, service entrance conductors can be spliced and tapped according to certain rules. Conduit boxes and fittings should be installed at each conductor splice point. And so that shrink wrap tube that has a terminal for tapping a splice together, you know, that might not be a box or conduit fitting at your service entrance conductor splice point. And so that very easy tool that you can use for splicing cables together that you can find at Home Depot is not listed for service entrance conductors, so it cannot be used on your solar array. It's not listed for feeder conductors. It cannot be used on your solar array. Unless it was listed, and then it could be used. So here's a definition: fitting an accessory such as a lock nut, bushing, or other part of a wiring system that is primarily intended to perform a mechanical rather than an electrical function. And so we have a box, a junction box, and you have a conduit going in one side, conduit going in the other side. Then you have all these different kinds of product for that penetration to be made. And it depends on if this box is a metal box or a plastic box, if this is PVC, plastic conduit, or metal conduit. It depends on, you know, if you're using concentric knockouts where you have to ground the metal conduit to the box, or if you're just using the non-concentric dedicated outer perimeter knockout and completely filling it up, at which point you may just need a lock nut, which is kind of like a jagged washer that goes around, plus maybe a threaded fitting, and then a bushing to go over the threaded fitting so that your cable and your conduit isn't rubbing on any sharp edges. So you might have 3 or 4 pieces that include this, that attach this conduit to this box. They're all called fittings. And generally, general electric contractors know what to do with fittings. These are your Home Depot items that are commonly found, you know, off the shelf. Some requirements for physical damage. So let's see. So there's different requirements where, like, if you're doing an underground service entrance, you can do a direct burial requirement. But if it's not an underground service, you have to protect your service entrance conductors from damage. But that could include, you know, PVC conduit. There are support requirements for your service entrance conductor. So within 1 foot of every service head, gooseneck, raceway connection, with the intervals not to exceed 30 inches. And so for your solar array, here's a support requirement. You know, you need to attach that gooseneck to the building within 12 inches for your above ground entrances. You know, when your conduit is coming up from the ground, it needs, you know, if it's a 3 foot tall conduit coming out of the ground, it needs 2 attachment points, or I guess that would be 42 inches. So 3 feet, you might be able to get away with just 1 secure if you really want to. And what's common up on the rooftop is you get these rubberized conduit support fittings, and we've actually used these to support not just conduit but entire roof-mounted solar arrays to give that solar array some additional roof clearance. These are pretty heavy devices, and it turned out that building a racking out of these conduit supports and unistrut eliminated the need for concrete blocks on the rooftop because they were sufficiently heavy enough to hold the array onto the ground. So you look at all these solar designs where you're putting concrete up on the rooftop. It's like, well, why can't we put that additional weight to work by making the solar design more feature rich? I guess that's for another class. So here we have a gooseneck entering the building through requirements for that. We see this drip loop requirement. So you might say, well, that's a tangle of wires and it's a mess. Well, the reason is you have this overhead exposed wire. It's going to get rained on, and they want the rain to come and fall off the wire before it gets to this tap connection, and they don't want that water also going into the building. So you have to arrange your raceways to drain when going into masonry. If you're doing a ground mount and you want to put a raceway through some concrete, you want to angle that raceway so that water from the ground doesn't go into your raceway, but would rather drain out of your raceway. So then we have service equipment. Energized parts should be enclosed or guarded. Enclosed means not exposed to accidental contact. Guarded means not enclosed, but inside a panel board. You're allowed to provide a locking means. What that means is if you're doing, say, a ground mount solar array, you often will get a lot of empty space under the ground mount. And if you're doing a ground mount solar array along the side of a road, you can say, well, what would prevent anyone from just walking up to the ground mount and sticking their hand underneath? And who knows, there could be a safety condition going on. So do you need to protect a ground mount solar array with all these live exposed, feeder equipment going in? And yeah, and they make nettings that can surround a accessible ground mount structure to kind of prevent people from getting underneath it. Disconnecting means, the same 6-handle rule makes another appearance. So here's an example where we have where this is for a ground mount single line diagram, and we have our main disconnect switch here. We also have another main breaker switch here, so we could put tons of switches along this board if we wanted to, because it's protected by that one main switch. So you could flip one switch and turn everything down the line off. And we see the reason why we have this main breaker here is because we have 7 inverters coming in. So here's our 7 inverters, 1, 2, 3, 4, 5. Oh, well, actually, this kind of got into our design here. This is a 3-phase electric service, and there's 6 inverters here. So each inverter is taking up 3 legs of power, and that means on a panel board that's about 18 switches. And you might be buying a panel board that could be 30 switches or 40 empty spots. And so the question is, well, if you have all these empty spots, is it better to use the empty spots or not? And the difference is if you fill up all those empty spots on your utility scale design, you may have to specify a panel board that also has a main breaker switch. And so we've kept our string inverters to 6 so that we don't need to have a main breaker on this panel. We can just turn each inverter off at the panel using these breakers. Now, by the time we get these panels back to the main, where they're being combined, if we have, 7 of these distribution panels on site, if there's 7 distribution panels coming in and each landing on a breaker here, and just kind of ignore the ratings for the time being, but if they're landing on the breakers here and there's more than 6 of them, then we need to have this main breaker. And then the utility came in and said, we are going to require, it was kind of funny on this ground mount, the utility, it was a 1600 amp ground mount. And the utility said, well, we have this knife switch disconnect requirement. But knife switch disconnects only go up to about 800 amps, and then they're 6 feet tall and look kind of ridiculous. There wasn't a 1600 amp knife switch disconnect. At that point, you get into big boy electrical equipment, and you might have just a main switch that's not a knife switch. And so to avoid the learning curve and going back to the utility and saying, no, we don't need, can we get around your program? Because it was the solar program, incentive program that required the knife switch. We just divided it into 2 800 amp arrays with a knife switch disconnect, and it just wasn't a project issue. Your transformers get into this issue too, where you can be tapping on multiple services onto a transformer, and each of those services can have their own disconnect switch, provided that they're grouped in the same area and that they, if there's more than that, then you have to combine those services together. And so to kind of visualize what we're talking about here, we're all used to seeing our residential panels with breakers on them and then a main switch. You can also find distribution panels that just have slots for breakers on them, where you don't have to buy, where there is no main switch. And guess what? Those panels are cheaper. So if you can get away with a cheaper panel that just might be a distribution panel for solar, you can do that. You don't need to have a main. It comes down to that 6-handle rule making another appearance. A disconnecting means of listed equipment shall not be considered as a service disconnect for these kinds of devices. So this is where that external disconnect switch comes into play. Your on-site power generation disconnects, the disconnects that are integrated into the equipment shall not be considered the service disconnect. Now, that doesn't mean that the breaker on your panel board couldn't be considered the service disconnect switch. So if you're running to a generator or a solar inverter that has its own internal disconnect switch, the intent is that you have an external switch that can kill the power at that point so that you can service the equipment. If you kill the power inside the equipment, then you still have this hot lead coming in to the equipment, and that's not particularly safe. Your service panels are the same way. You can kill power to the panel at the switch and kill power to the whole panel, but you still have hot power coming into it. So that external disconnect switch requirement is there so that you can have people accessing the equipment and servicing it without electrocuting themselves. And eventually that safety issue makes another appearance on your main service panel. And lo and behold, we have these requirements where, only with going and pulling a permit, maybe you can pull a permit yourself, depending on your state, to work on your own home, or maybe you have to go through a licensed electrician in order to access the back of your main service panel. And the reason is because it's not safe to do so. It's always going to be hot unless the utility comes out and trips that fuse up in the power line, which only takes them about 5 minutes to do. Usually on a residential job site, the utility will come out and de-energize your home for free. But electricians work inside those hot service panels all the time. But that's to some extent, it's not a good idea. To a lesser extent, they do it because they're familiar with staying out of the top of the panel and just working at the bottom of the panel. So going into a building, coming out of one electric service, you can have 2 to 6 disconnects permitted for your general service requirements. And then you can have additional handles permitted for additional service connections or special use cases like backup power supplies. It says only the following equipment shall be permitted to be connected to the supply side of the service disconnecting means. What does this supply side of the service disconnecting means actually mean? Well, we have our utility meter, and then we have our main service panel with our breakers on our main service panel. And then you have your main breaker on your main service panel. This main breaker is the service disconnecting means. And so connections to the supply side of the service are not on the utility side where you have your transformer and your power lines, but this section right here is considered to be on the supply side of your electric service main disconnecting means. So this is actually going up through the main disconnecting means. This is the supply side of the main disconnecting means. And in the solar industry, we talk about supply side taps rather than load side taps, where you can connect a solar array or a battery bank or a generator protecting a critical load panel on the bottom of that bus bar, or you can connect it up to 100% of your electric service on the supply side connection. Lo and behold, what we're allowed to connect certain equipment on the supply side, and that would be energy management devices, meter cans and meter boxes, disconnect switches, load management devices, surge arresters, stuff that has to do with your on-site electrical generation can be connected to the supply side of your electrical service. That just makes obvious sense. It may not make sense to your local inspector. If you live in a rural area and they've only been doing smaller solar arrays without batteries, maybe the local installer in your area is only doing load side interconnections and not supply side interconnections. And so maybe your local solar rebate program has only been doing load side interconnections because your local solar rebate program is being run by non-electricians and they're just copying off each other's homework and passing this load side connection requirement down the ranks. By the time solar gets to your local building permit office, the electrician assumes the solar program, who knows more about solar technology than they do, knows what they're doing. And so by the time you want to do a supply side connection at your local office, you call up the permit office and they say, well, we only allow load side connections. You can't do supply side connections for solar. At that point, it really helps to refer them to National Electric Code and say, look, if we were doing a whole house generator, how would we interconnect it to where would we land it? Well, it's that same supply side connection. And so if you can get them saying, well, yeah, we allow, whole house generators to be connected through an automatic transfer switch, and you say, well, we're doing the exact same thing as that, all of a sudden, they realize that their load side connection requirement is ridiculous, and you can start doing supply side connections in your area, even if you're the first to do it. So we got solar being allowed to be connected to the supply side connection. It's really not that big of a deal to do supply side connections, and we've kind of talked through that already. We got short circuit current rating, the current at a nominal voltage to which an apparatus or system is able to be connected without sustaining damage. So that's during a short circuit current, if the cables or equipment could be sized to short out but still work. Overcurrent would be less than a short circuit current. It doesn't, you know, your short circuit current could be 100 amps, but you're putting it on a 20 amp breaker because it's not supposed to have 100 amps. It's it's supposed to be at 15 amps. And so, you know, you have short circuit conditions. You could also have overcurrent conditions that are less than your short circuit conditions. And then you can have overcurrent protection devices that are not just preventing against short circuits, but overcurrent conditions as well. And what is an overcurrent protection device? Well, it could be your breaker and your main service panel. That 20 amp breaker is a main current device, or it could be a fuse. You know, it might not be designed to be reusable. It, you know, if you have an overcurrent problem where you have switches in your panel just resetting all the time, you know, you need to get that looked at. And so there are some advantages of having a fuse that during an overcurrent condition will just burn up and then not work anymore until someone comes out and actually looks at it, rather than just having a client be able to reset the switch and see if the problem happens again. And where I've seen this happen is up on the rooftop in your combiner box, where you have and this isn't very illustrative of it, but you would have in a combiner box, you have multiple circuits going in to the box being combined into one set of wires going back to the inverter. Or maybe you're doing the combining at the inverter itself, but there's no room to fuse the circuits on the inverter, and so you go up to the rooftop and fuse the circuits at the rooftop, even though you're not combining. And why you might want to do that is maybe your combiner box, maybe your inverter can track multiple circuits, and so you don't want to combine them together up on the roof. You want to keep them separate, but you still have to meet rapid shutdown requirements and these fuse requirements. So there's a room on a box for room on the rooftop for a fuse box, where you're taking all the circuits into the fuse box, fusing them, and then letting the system operate. These fuses should never burn up. You know, you should not have an overcurrent situation on a properly sized solar array. You know, what I saw is the way you do these fuse sizes is you take your amperage and then you multiply by, you know, 1.25, and in solar you have this other additional 1.25, and that gives you your new amperage, and then you round up to the nearest fuse size. Well, I've seen an instance where the solar installer, that calculation was right on the border, and I don't know what happened. Maybe they went to Home Depot and got some fuses, or their electric supply store, and there were only 5 amp fuses or 10 amp fuses available instead of 15 amp. And the installer thought, well, normally this fuse will never get up to 10 amps, so a 10 amp fuse will be fine. You know, at this calculation might give you 10 amps versus the additional safety factor giving you another. Regardless, I got called out to site to troubleshoot an array, and it turned out that the fuse in the fuse box was too small to accommodate this additional 25%. And what had happened was, on the very hottest day of the year in the middle of summer, you know, you go and look at your spec sheets and you see how temperature affects voltage and amperage. You know, temperature, heat causes voltage to plummet, but amperage will actually uptick a little bit. And in other classes, we look at the order of magnitude, and it's like for every increase in 1 amp, your volts drop by 10. And a volt times an amp is a watt, and so heat ultimately is going to plummet your array performance, but it will increase your amperage a little bit. And so on the hottest day of the year, because this fuse was not designed to take the additional 25%, that fuse was undersized, and it blew the fuse. Well, all that happened was we got up on the rooftop, swapped it out with a 15 amp fuse instead of a 10 amp fuse, and the system went along and worked its merry way. It wasn't like the installer had inserted a safety hazard into the system. It was just, a slightly undersized fuse. And that was good. The system had a wrong component that was designed into it, and because it was a fuse rather than a breaker, it required someone to come out and actually diagnose the problem rather than just reset the problem. Likewise, you might get into a situation where you have a single inverter, and then there's no external disconnect switch, and you're plugging that thing right into your supply side connection. So here's your transformer, here's your load panel, you're doing a line side tap with one inverter, and the question is, well, the utility wants me to do a knife switch disconnect. I have to have something, I have to have some kind of disconnect, so why don't I do a knife switch disconnect? And I still need an overcurrent protection device. And so the answer is, well, you could put a panel with a breaker and then have that be your a panel with a breaker would be your disconnecting requirement. Or you could do a knife switch that's a fused knife switch. Both the breaker switch and the fuse switch are overcurrent protection devices. And these systems, it might be that your external knife switch with a fuse is your cheapest pathway. You might not need an actual panel just for a single inverter system. Okay, let's see. So both breakers and fuses are overcurrent protection devices. For products that are rated at 800 amps or less, you are sizing to the next highest overcurrent protection device. But once you get past 800 amp solar design, when you're doing initially your breakers are like 15 amps, 20 amps, 25 amps, all the way up to 50. And then you start going up by increments of 10. Your breakers are 60 amps, 70 amps, 80 amps, all the way up to 110. And this is just a matter of convention. But we got a 5 amp difference in your breaker sizes, a 10 amp difference in your breaker size, 25 amp up to 250. And then we start getting into 50 amp breaker size differences, and then 100 amp breaker size differences. And as soon as we get past 800 amps, now our breaker sizes start going up by 200 amps, 200 amps, 400 amps, 400 amps, 500 amps, and then 1,000 amps. If we were just saying, okay, well, our system is operating at 2,900 amps, and then we apply a 25% overcurrent protection device, and so that'll get us past the 3,000 amp mark. And so we're gonna protect our 2,900 amp system with a 4,000 amp breaker. That could mean that your system might be operating at an amperage that is 30% higher than what it's intended for, and it's a high power device, and that could be dangerous. When we're talking about little 5 amp or 10 amp or 25 amp differences, that's less so. So when you're doing circuit sizing of 800 amps or less, you're taking your output amperage or your effective output amperage, multiplying by 25%, and then rounding up to the nearest breaker size. When you get into higher amperage circuits beyond 800 amps, it might be that you are sizing the breaker to trip before you get into this additional protection so that you don't burn up your wires. Now these fuses and breakers, you may be required to have a main overcurrent protection device, but then you'll find that there's fuses and other overcurrent protection devices in your system that might do other things. Like if you want to do a combined run where you have multiple circuits being combined into one wire, maybe that occurs in a box in the roof, maybe that occurs inside your inverter itself. but you need to have additional fuses there so that if there's a ground fault, if this ground faults, and maybe another circuit is ground faulting as well, you don't want your 3 circuits of power to outflow through that ground faulting single conductor, because now you have 3 times the amperage flowing through the wire. And so you might put additional fuses into your circuits to provide additional layers of protection. That these kinds of fuses are not a substitute for your main overcurrent protection device. At the same time, they're not subject to the same requirements, so that readily accessible main overcurrent protection device does not need, your roof-mounted combiner box does not need to be readily accessible simply because it has breakers and fuses inside of it. It needs to be accessible, but not readily accessible. You might need a ladder to go get up on it. You might need a screwdriver to get rid of the panel that's covering it to access it. You may need a screwdriver to take the lid off and access it. It's still accessible. It's just not readily accessible. But your roof-mounted equipment does not need to be readily accessible, as long as there's a main overcurrent protection device elsewhere. That is. Let's see. Ungrounded conductors have overcurrent protection devices as well to prevent overcurrent situations. Battery conductors, overcurrent protection shall be permitted to be installed as close as practical to the storage battery terminals in an unclassified location. So often your battery overcurrent protection devices are just the breakers and the DC breakers and the service panel the batteries are landing on. No overcurrent device shall be connected in series with any grounded conductor unless it opens all the conductors of the service, including the grounded conductor, so that no pole can operate independently. Whenever you're upsizing your cable, and so that often happens in solar, you'll do your voltage calculations, your line calculations, and you might say, well, up on the rooftop, especially the NEC has changed their temperature requirements, where you used to have this chart of, if you're a ½ inch above the rooftop, if you're a ½ inch to 1.5 inches, if you're above 2 inches for changing the ampacity of your wire. Now it's more like if you're below a ½ inch versus above a ½ inch. But it's often required to upsize your conductors, even if you don't have the temperature, the reasons to upsize your wire because you have all these temperature degradation factors going into your amperage capacity. But if you have no change in your amperage, and you might say, well, all I need to do is number 14 gauge wire for this solar application, most solar installers are still going to upsize to number 12 or number 10, because just because you have to design for this ampacity, or you have to design for a 3% voltage drop, that doesn't mean that hitting a 2% voltage drop or a 1% voltage drop, that doesn't mean that taking less resistance out of your system is a good thing. I mean, think of how much more money you would spend on a high-end solar panel that is more efficient than a lower-end solar panel. You might spend hundreds of dollars to go for that top shelf panel. It might only cost you $40 to get the same efficiency gain by upsizing your cable. And so just as a standard design process, it's common in the solar industry to see upsized cable, and for that matter, upsized conduit, because you might only have to have 3/4 inch conduit, but there's might be more knockouts for 1 inch. If you go into that 3/4 inch concentric knockout, you might have to use grounding bushings. just keep that extra space in the conduit is going to make your electrician happy. And so you're upsizing your cable and you're upsizing your wires just to gain project efficiency. Well, whenever you're upsizing those wires, you're also increasing their amperage capacity. And so, you also have to increase the size of your drain in your system. So when you are upsizing your grounded conductors, your ungrounded conductors, like your power cables, you also want to upsize your ground and neutral. Now, you're not required to upsize your ground and neutral. You're permitted to. So there's certain cases where, like that DC bare copper ground of number 6 going up to the rooftop to ground your system, that's more than sufficient. That's to ground your DC solar racking. So you don't necessarily have to in all circumstances. And so in your balance of system material, you go to Home Depot, it's common to find wires where you might find that you need a number 8 cable, and the only Home Depot wires there have a number 8 positive, a number 8 negative, and then a undersized ground or an undersized neutral. That may or may not work for your system. Okay, so accessibility, your breakers and switches should not be more than 6 feet 7 inches above the floor or working platform. So when you're doing your electrical design layouts, the general philosophy is make sure that you have enough working equipment so that anyone can access the switches and handles, and also make sure that your non-electrical scope stays far away from your electrical scope. We see requirements like on the outside of the building, the stuff being a 3-foot distance. It's not so harsh in your control room. You need that 30-inch width working space in your electrical zone. But generally, you don't want to combine. You want to keep your plumbing away from your electrical. You want to make sure you have plenty of space to operate, and then you won't get any code violations in your array layouts. It gets harder when you don't have unlimited space to deal with. Let's see. So we've covered a lot of these positionings. Vertical positions and closures for overcurrent devices shall be mounted in a vertical position unless impracticable. And so, if you have a service panel with a main overcurrent device, that's more important to be up and down than your side-mounted breakers plugging into that device. So your side-mounted breakers are allowed to be left and right because it's impracticable in your service panel design to have a main that's up and down and side breakers that are also up and down. But if it's the choice of, if you have a knife switch that with a handle on it, or even just a single service panel with a single breaker switch on it, it should be mounted so that that breaker is going up and down rather than left to right as a standard layout. So now we're going to get into grounding and bonding. And remember, bonding is making sure all the metal parts have continuity, and grounding is making sure they're connected to ground. So grounding and bonding are essentially the same thing. We have this bonding supply side jumper that connects the neutral to ground. We have what's called an effective ground fault current path, which is an intentionally constructed low impedance path to carry current from a ground fault into the ground, and also will trigger your ground fault detection systems. Then you have the path that the electricity could take. It might not be the effective path that you want it to take. Any path that's conductive from the ground fault So we have grounded systems will limit the voltage imposed by lightning, surges, or unintentional contact with higher voltage lines, and stabilize the voltage to earth during normal systems. So, we want any stray voltages to go to ground rather than go into the rest of our electrical system. I guess that's kind of obvious. One thing that I can think of that you might need to check when you're in areas of kind of more compact soil types. We were driving the ground rod in our off-grid home, and in Mississippi, you get this rock shelf underneath your soil. And so that was preventing the ground rod from going all the way down to depth. And you're allowed to angle it and eventually lay it down on its side. And but the problem is, this concrete barrier of soil, there might only be 3 feet of additional mud. Well, this mud is pretty dense too, and it's more insulating than conductive. And so it was hard to establish an actual reference to ground where if we were trying to ground fault, the voltage was not actually quickly draining the ground. And so after driving 3 ground rods into the ground, eventually we had to dig a trench and just bury some copper wiring down into the ground and go well above and beyond the requirements of code, just so that for our specific soil type, we had an effective ground path. And we had to increase the surface area. So generally, you're going to connect to your ground rod, your copper wire. They call this an acorn, and it's just a lug, but that has to have a protective barrier around it. You might just cover it with PVC and put it into the ground. We have to remember that our metal parts are given a anodized coating so that they can be protected from the elements. But that anodized coating also increases the resistance of metal so that just doing a metal-to-metal connection is no longer grounded. And so when we're installing our grounding washers between our metal module frames and our metal racking, there's a few things you want to make sure to do, and one is to make sure that these surfaces are clean, and that clean is to make sure that these grounding washers are flush, and then also these grounding washers have little spikes that go into the metal to ground, and you need to make sure that they actually get in there. And so, if you're installing a module and using a grounding washer, and then later you take the module off and you look at where that grounding washer is and you don't see any indentations into the metal module frame, then you probably don't have that metal module frame being grounded. So you can do continuity tests on site to make sure your system is properly grounded. Let's see, we have AC systems are grounded. DC systems shall be permitted to be grounded, but they don't necessarily have to be grounded. The DC side could be completely isolated from the AC side. And then you just need that positive-negative reference. But that still doesn't mean you don't have to ground the metal parts that are not part of the DC power system, that are not intended to be current carrying parts, but they're still metal parts exposed to current up on the rooftop. Just because you have a DC system that is ungrounded, that's more of an energy processing term for the inverter that doesn't get you out of your system grounding requirements. On the load side, A neutral shall not be connected to equipment grounding conductors or reconnected to ground on the load side of a service disconnecting means unless otherwise permitted. So all this talk of bonding the neutral to ground, generally speaking, you don't do it. Generally speaking, that we've already talked about it, so I'll keep going. There's an illustration a little later. Then we start getting into unspliced bonding connections. We have an unspliced main bonding jumper shall be used to connect the equipment ground conductor and the service disconnect enclosure to the neutral. So just that one section where you're connecting the neutral to ground, that needs to be an unspliced conductor. The neutral needs to be routed with the ungrounded conductors. So it's not like you're going to have conduit where you have the power lines and then you put the neutral separately. Now, DC systems, you don't have the neutral, and sometimes you have to install a neutral, but it's more for a communication than to actually be a neutral. Let's see. For a single raceway, shall not be smaller than 12.5% the area of the largest set of service entrance conductors. I don't know. We'll get into conduit sizing a little bit later. Parallel conductors for 2 or more raceways. If the ungrounded service entrance conductors are installed in parallel in 2 or more raceways, the grounded conductors should also be installed in parallel. And I think what's important about this is you might find in your designs that it might be easier to do 2 runs of 4-aught cable or 2-aught cable than to get up into your more industrial cable sizings. Like 250 kcmil is fine. I've even done wire runnings of 750 kcmil, which is about as high as it gets, but it wasn't worth it. It wasn't worth it just to have one cable and one conduit that's a very heavy, tough to bend cable. We should have just broken it into 2 smaller cables and done a parallel run. The problem is when you're doing parallel runs, you can't just have one run for your grounded conductor and then, that might be a smaller size and then leave it out of the other run. You need to run your grounded conductors in parallel as well. We already defined the grounding electrode conductor. You have your grounding electrode conductor is the conductor that connects to the grounding electrode. AC systems, the conductor to be grounded is the neutral conductor, is the grounded conductor. On a 2-wire system, you're either connecting the positive or negative to ground. And again, all of this is so that you have an electrical flow all the way back to ground in your electrical system. Either the neutral conductor is carrying imbalanced loads to the drain, or on a 2-wire system, you need electricity to drain just so it has somewhere to flow to so that it can do work. But that doesn't mean that your grounded conductor is connected at multiple points to ground. It's connected at one point to ground. There are some minimum size requirements for your neutral. It says an on-site interconnected solar battery is not separately derived if the neutral is a service neutral. Transfer equipment might not include a switching action in the neutral conductor. So we talk about separately derived systems. even though your neutral may not be intended to carry current at all times, you know, maybe it's undersized, maybe it's only designed to carry unbalanced loads. But at one point, if you have a transfer switch, you will be, if you want your solar array to be interactive with the grid, it's going to be sharing the same neutral as the grid. And you might have a switch that disconnects the grid feeders from your solar array feeders during a blackout, but you may want to switch back onto the grid automatically when the grid comes back on. And so you're sharing a neutral to provide, you know, a common reference point for grid interactivity. If you're sharing a neutral, it's not considered to be a separately derived system. So now we get into the system bonding jumper. We've already talked about this. It's that connection from neutral to ground. The building grounding electrode shall be used as the grounding electrode for a separately derived system. If a separately derived system originates in equipment that is listed and identified for use as service equipment, the grounding electrode for the service equipment shall be permitted to be used as the grounding electrode for the separately derived system. So, you know, what if you have a grounding electrode that is out by your point of service entrance, and then you have a whole building supply generator? You know, you may want to drive a separate ground rod and use that as the grounding electrode if your system is being placed in an off-grid mode on a frequent basis. And so you're allowed to have a separate grounding electrode on your building for use on separately derived systems if your equipment is listed for that. You might have two parts of the building that are on completely different electric services, and you may not want to run the all the way back to the building's original grounding electrode. It may not be a grid connected system. It may just be running on batteries and a solar array and a generator. So there are exceptions to not connecting everything up together. So a common grounding electrode conductor shall not be smaller than 3/0 copper or an eligible water pipe or the metal framing of a building or structure. So it's common to see 3/0 grounding electrode conductors. Then table 256.6 is used for sizing that. We're not at that point yet, so we're getting there. Generally, you're sharing the grounding electrode. So if you have a ground rod already on your building, you're using that as your grounding electrode. Although in solar design, you run 2 ground rods, and so if you only have one, that's a good opportunity to put in another. It's much easier to drive your ground rods when you have mechanical equipment on site, like a forklift or something like that, where you can, you know, use equipment to drive the ground rod into the ground rather than a sledgehammer. Now we get into our sizing tables, and you know, we see for ungrounded systems, an equipment grounded conductor shall be installed with the supply conductors and connected to the building or to grounding electrodes. So, you know, even if your inverter is an ungrounded inverter, you still have an equipment ground conductor. When supplying multiple buildings and disconnecting means located on the same premise, the connection of the neutral to the equipment ground conductor at the separate building shall not be made. So if you're designing a microgrid and running multiple buildings off the same microgrid, you know, you still only want that one neutral to ground connection. An equipment ground conductor for grounding is installed between multiple buildings, and grounding electrodes and separate grounding electrodes are installed. A connection is made at each building between the equipment ground conductor and the grounding electrode. So I guess these are different ways that you can ground. So you're still connecting your equipment ground conductors between the multiple buildings, and you may be installing grounding electrodes at multiple buildings so that your ground is at a zero reference point. But as far as carrying the neutral and connecting the neutral to ground, you're still you're making sure your ground reference is at ground at each building, but you're still carrying your neutral reference all the way back to your main source of supply. You're doing your new construction design, or you may find that the building does not have sufficient path to ground, or even you might need what is more common is you'll find one ground rod on site, and you may need to install a second one. So there are a few instances where you're going to be in charge of speccing out the grounding electrode. On a ground mount system, you may want to put a grounding electrode out on site, not a neutral to ground connection, but a separate grounding electrode. And so what constitutes a grounding electrode? Well, there's a few things that do. A metal in-ground support structure. That could be like a pile. So you're driving a pile from your solar ground mount into the ground. Well, guess what? Most solar piles do not have 10 feet or more of depth into ground. So when you're driving a pile into the ground, that commonly does not qualify as a grounding electrode, even though you think, well, certainly this pile is grounded. It may not have the surface area required. A metal pile may have galvanized surface treatment, drastically reducing its resistivity. So even if it's 6 feet into the ground in a 6-inch wide pile, it may not have the surface area required to quickly clear current or voltage into ground. A concrete encased electrode. So what's common for a grounding electrode is to use the rebar in your concrete and to say that that's the grounding electrode. But the problem is that rebar has to be a half diameter in size. And so what's more common is you take some additional bare copper wire and just throw it down into your foundation as well. But the thing is, concrete is less conductive than normal surface dirt, your clay and sandy soils. And so instead of just having like an 8-foot copper ground rod or a 10-foot metal pile, when it's going into concrete, you have to have additional material in that concrete for it to be considered a grounding electrode. So what's generally common is that you have a ground rod going into the ground. But one problem with ground rods is that they have to be driven 8 feet into the ground, and that can be a difficult task in many areas. And so there's other ways to build grounding electrodes, but if you're using kind of the official, hey, if you can drive a ground rod 8 feet into the ground, then that's the best way to do it. If you're using a ground rod or a ground pipe, often you'll get more leeway in the size of your equipment and ground conductor than you would with where you're like making your own kind of grounding electrode out of bare copper wire by digging a trench and burying it directly into the ground. You can, or you're taking a bunch of bare copper and throwing it into the foundation of your house. That might not be as conductive as using a ground rod. And so if you can use a ground rod, you should, is the short of it. If you have the opportunity to put a ground rod there as your grounding electrode versus any other thing, it's only in the circumstances where, your house is 3 feet down from your house is a concrete shelf that you can't bust through. So you have to make your own kind of ground ring or go away from the off-the-shelf parts into more homemade solutions. You don't want to be there as a starting point. You want to be there because you have no other options. Using a ground rod or a ground plate is the common way to do it. Because not always is that building going to be qualified as a grounding electrode. So then we get into not just your grounding electrode, but a supplemental grounding electrode. And what's that? Well, you need an extra one just in case. Supplemental ground rod required, and it's required when you're required to have a supplemental electrode. You can, a common way is to take your existing ground rod and then to drive another ground rod right next to it and bond them together. Or you could connect it to your grounding electrode conductor or a grounded service entrance conductor. So, you might be required to put in supplemental grounding electrodes with separate requirements for what constitutes a supplemental electrode, and there might be a little bit more leeway in there than in your primary electrode. But again, your ground rods, pipes, or plates bonding jumper is required not to be larger than number 6. So if you're using a ground rod or a ground pipe or a plate, that bonding jumper is not required to be larger than number 6. So it's very common, given that there's that number 6 bare copper wire up to the rooftop requirement, just to run number 6 bare copper up to the roof from your ground rod is a common design requirement. So I think this should be not roof, but this should be rod and pipe electrodes. There's a procedure for determining when you can't drive that ground rod into the ground. The proper order is to first try and drive it at a 45-degree angle. And then if you can't drive it at a 45-degree angle, you need to dig a 30-inch deep trench. And the only way to dig a 30-inch deep trench, in my opinion, is to rent a trencher. Often when you're doing these kinds of dirt work projects, you're doing a ground mount array. And if you're ordering a Bobcat to help you with your ground mount augering, ordering a trencher along with that doesn't really impact your budget all that much. Your grounding electrode should be common across a single building, but we saw that there is an exception for separately derived systems. Not exposed to physical damage, and if your grounding electrode conductor. So remember, your grounding electrode conductor is what connects your building grounding system to the ground rod. It's the last leg of the journey to your ground rod. If it's smaller than number 6, you have to protect it and conduit. If it's larger than number 6, you don't. It can just be, so you might look at a building and say, well, why is that ground wire exposed? Why is it just hanging out on the side of the building? Well, it's because it's number 6 copper or larger. Now, whether or not that looks better or worse than protecting it is a separate issue. So the main thing about this grounding electrode conductor, so remember this is the last stop between the grounding system and the ground rod, is that it needs to be continuous. So does your equipment ground conductor need to be continuous? You know, that green wire that in your outlets, it's what's the shape of it, like a domed square? You know, does your ground need to be continuous throughout your system? No. You take a metal conduit and a lock nut and you land on a metal box, and then you're on your metal box, and then on the other side you have a listed for grounding lock nut and fitting with the rest of your metal conduit. You know, those are all splices or taps, for a lack of a better word, where you have non-continuous equipment grounding occurring. But on that last stop between where your equipment ground conductor is all interconnected, and that can be at any point on that equipment ground conductor system, but that last leg of the journey between the equipment ground conductor system and your grounding electrode conductor needs to be continuous. And that's almost kind of weird, because you could have you know, imagine your building to be a big square, you know, and this can be at any point off that square before you get to your ground rod. But it's just saying there's more robust requirements for that last leg of the journey to make sure that that never fails, and that if you have a ground fault situation, that it's properly sized so that it doesn't heat up, so that it can clear the ground fault without burning your building down. So that needs to be continuous. And there are you can take bare copper crimp tools to permanently crimp the copper together. I can tell you that it's nowhere near as good as designing your building so that you don't need to do those permanent crimps. But what it is you might be wanting to ground your whole solar array together. And so you're saying, well, does that mean I have to run, if I have bare copper wire up to the array, do I have to run that bare copper throughout the entire array without splicing or crimping it? Well, it depends if it's the grounding electrode conductor or not. The grounding electrode conductor can just run up and lug on to the end of the racking. And if your modules are bonded to your racking, then no, you can just, you know, make a bonding jumper from that point to make sure all of your equipment's connected together. But that last leg of the journey needs to be a continuous run. And there's different ways to make that continuous. If you have to splice it, there are ways to splice it, such as irreversible crimps or sections of bus bars connected together. You know, what I have seen solar installers, they take this continuous grounding requirement, and that makes them afraid to cut any conductor and do any kind of splice or tap across a wire. Let's see. There's sizing requirements. Table 25066. You know, just what's common on a grounding electrode system is to run bare number 6 up to the rooftop. If you want to put it in a green sheathing, just you're allowed to. It doesn't have to be bare. It can be bare. And so what we see is the grounding electrode conductor that connects to the ground plate. It can be number 8, as small as number 8, but it doesn't have to be. And so often the sizing of this grounding electrode conductor will say, well, it needs to be number 8. There's nothing wrong with upsizing it to number 6. And so you could have number 8 in a green plastic, but then it has to go inside of conduit, and that's just as good. But or you could have a bare number 6 run up to the rooftop, and it kind of blends into the building better and is a little bit easier to tuck away behind whatever other conduit there is, or your bare number 6 snaking down the side of the building could look bad. You know, there you get a lot of flexibility in what you want to do. The easiest way is just to run bare number 6 up to the rooftop. You could run that internally as well. It doesn't have to be an external run. So all your metal parts need to be grounded. Metal components that are installed in non-metallic raceways, like a piece of PVC conduit, that are isolated by contact to any other metal parts, don't necessarily have to be grounded. So if you have a splice kit that's listed to fit inside of that shrink wrap splice kit, if it's listed for utility service conductors and feeders, you can put it inside a conduit as long as there's no metal within 18 inches of that connection. So metal parts need to be bonded. We've talked about the concentric knockouts. It's kind of moving us into towards our wiring discussion. There may be some additional connections that are required for higher voltage components. So what's common is to use metal conduit with compression connectors and lock nuts. There are sizes for that bonding jumper on the neutral. We'll have a picture of it a little bit later, but there are minimum sizes for that. So just in general, if you're installing metal equipment, you have energized wires inside that equipment, that metal equipment frame is going to be connected to your grounding system. And while it is possible to have your conduit, your metal conduit, qualify as your equipment ground conductor, what is more common is just to run a equipment ground conductor cable along with your solar array, so you don't have to worry about the exceptions. In terms of when you're running equipment ground conductors, if it has to be either bare or green until you get into larger cable sizes. So once your cable sizes become sufficiently large, you can just use black cable and tape it. But if you're in like number 6 or number 8, you're putting a jacket all around that cable, then it has to have green insulation. I think that using colored jackets on your cables looks really good and helps out the crew. On the solar end of things, you can get a red and a black jacket that for your positive and negative cables, and it just helps keeps things clear. So you can run equipment ground conductors when it's number 8 through the framing members of your structure. So what that might say is if you're going inside the rooftop, inside the building to ground your system up to the rooftop, then maybe you're using a number 8 with a green jacket rather than bare number 6 when you stay outside the building, so that you can run it through your framing members. And what I usually do, will just put the number 6 in the conduit, an oversized conduit. let's see. Let's kind of move away from the grounding issues. So we get to this table 250-122, the minimum size of the equipment ground conductors, and it's basically it's just based off fuse sizes. The solar inverters, like microinverters, are 20 amp circuits, and then most battery and residential solar inverters are up in the 60 amp circuit. And so you get this number 10, and you're often buying number 10 as your solar cable. So are you allowed to use that number 10 as an equipment ground conductor? Technically, no. It's smaller than number 4, and so if it's a insulated cable being used as your equipment ground that's smaller than number 4, then it needs to be in a green jacket. If it were larger, if it were number 4 or larger, you could just buy some green tape and tape it off, but you could fail inspection because of that. No big deal. Some solar inverters may be ungrounded, and the big thing is they just don't have a neutral. This graphic should be a lot more clear now in terms of what's happening at this point. So we have our grounded system, and then we have our utility service entrance, and in this case, our meter is being combined with our service panel. Sometimes you might have a disconnect switch right here, and you'd have the bonding occur in the disconnect switch. Or you might have a standalone meter case, and this bonded connection occurs in that meter case. Well, that's not what's happening here. Right here we have what's called a meter-base combo, where it's a combination load center and meter base. The meter is built into the load center, and we see a call out for bonding the neutral to ground inside this case. So if you're doing an off-grid system, you get to your, there is no meter, there is no utility connection. What you have is maybe an energy distribution panel before you get out to your load panel, and you will be bonding the neutral to ground inside of that energy distribution panel, or maybe you have a whole house generator inverter that is bonded to ground inside the generator, and that's providing your main bonding jumper connection to ground. If your generator is operating and its neutral is connected to ground, and it's not a separately derived system, but it's on they're powering the rest of your off-grid system, that's the only neutral to ground connection you want. If you want to grid connect it, then you need to be disconnecting and you're providing your own neutral to ground, you need to be disconnecting the utility neutral at that point in your disconnect switch. So here we see the structural metal frame of a building should not be used as the required equipment ground conductor for AC equipment. So you can't just ground your equipment to the roof and then consider it to be grounded. In fact, let me pull up a picture. This will be a little fun. Here's our off-grid photo where we have the metal roofing purlins, and then DC wiring has to be in metal conduit. And so we had to use metal fittings because we couldn't use plastic fittings. It's DC wiring going through the roof at that point. And this is not a non-metallic flex conduit. This is a metallic flex conduit. And you can kind of see the bending radius is kind of similar to what a field bended conduit would look like. So, you know, we're not gaining much in terms of bending radius. In fact, we couldn't just go straight through the Z purlin into the rooftop because this bending radius was physically required. It's not like you could just give it an extra oomph that would break it. You know, you're not allowed to install broken conduit on your job. We had to give it this 45-degree tilt. And so we can't just ground our conductors or our racking going into the rooftop to this. And so the question is, well, how are these couplings and fittings grounded? You know, what we have to do later, and let me pull up my pen. You know, these metal parts need to be grounded, and they're going onto this Z purlin. You know, what would be best is to get some grounding washers and on the inside of this roof, ground or put a little ground bar here, and come out with our equipment ground conductor. Get like a grounded bushing and put a bus bar here and ground everything together. And with our bare copper wire, land on this ground bar before going out and landing on our racking, you know, and actually grounding the and then I guess you get into this issue where you'd have to go through and ground each one. And so that, you know, you might actually find yourself taking some bare copper wire and just running it along the roof cap in order for this kind of specialty integrated internal conduit run to be code compliant. Of course, then we have the equipment ground conductors should be terminated inside of a box. All right, so you might say, well, can I just throw out the non-metallic, the metal box, and make it non-metallic, and just have a PVC box instead of a metal box on the roof, or in my equipment, not really worry about that metal box being energized and being a shock hazard. When you're going into a non-metallic box, you still might have to use metallic fittings, and those fittings inside the box still need to be grounded. And so you still might install a ground bar inside the box with a fitting that has a grounded connector onto it so that you can connect your fittings to ground. So, you know, going with the non-metallic box to save on grounding really doesn't save you anything, doesn't really save you all that much. You have to do additional work inside the box. Okay, so on premises, a grounded connection shall be made at the source, the first system disconnecting means, or by other listed means that's accomplished to accomplish equivalent system protection. And so you have listed ground fault protection systems that are not positively grounded that still get the job done nowadays. When we're sizing the DC current grounding electrode conductor, so where is our DC electrode conductor showing up? Well, you know, up on the rooftop where you have these metal, the system being exposed to metal parts, there's no AC equipment up there. You know, you technically that metal racking can be exposed to DC current. You need to connect it to the DC grounding electrode system. It may be the same as your AC grounding electrode system. You may be bonding the DC to the AC And you're going to do that down at your ground rod anyway. So can you bond your DC and AC grounding together? Yes, but you have to be aware that the DC grounding requirements may be a little bit different than the AC. The size of the grounding electrode conductor for a DC system shall not be required to be larger than 3/0, not smaller than number 8, not smaller than the neutral balancer on a 3-wire balancer set, not smaller than the largest conductor otherwise, not required to be larger than number 6 when using a ground rod. And so, you know, often we'll use a ground rod so that our grounding electrode conductor up to the rooftop is not required to be larger than number 6. And so, and you know, otherwise you might be sizing your grounding electrode conductor to be the same size as your largest conductor. Otherwise, on a residential system, that might be a number 10 wire, but on a commercial system where you're using combiner boxes, that could get up to you know, something much larger. Here we go. Let's see. DC ground fault protection is required, and you know, we've talked about how it used to be connected to the grounding system, creating a blind spot. An unspliced bonding jumper shall be used to connect the equipment ground conductor to the grounding conductor at the source of the first system disconnecting means. And so from the DC, you know, from the DC solar disconnect up to the roof, let's see, ungrounded DC systems supplied from standalone power sources should have a grounding electrode conductor connected to an electrode that provides grounding for metal raceways. All right, so you need to be grounding your systems at the source to the first disconnecting means. Usually your inverters are located, you know, right next to your energy distribution panel, which is also where your service is coming in. So this is not stuff that you need to worry about so much. All right, how do I erase these? There we go. Okay. Surge protection devices. So it's common to put lightning arresters on your equipment. It says where used, they can be connected to each ungrounded conductor. And so you'll get lightning arresters that are listed for particular services. And what that might mean is that if you're using a 240 volt split phase surge arrestor connecting to each leg of power, DC, you're connecting to each leg of power. Now you want to use a lightning arrestor that is marked or actually designed for your particular electric service. They cost about $20 or $30 each. Now this is for you ground mount utility scale guys. Metal fences and structures within 16 feet of your array need to be connected to your grounding electrode systems. Once you get into higher voltage systems, you know, the higher voltage you go, the more that electricity is going to be impacting the voltage of the immediately surrounding earth, and more likely it can arc out over longer distances. Erase. Okay, let me go to my questions. Technically, no difference between the DC and AC electrode system during bonding. What I have found is that when you're going from the DC side to the AC side, you're transforming the power, and so often you'll go from you may be going from it's more common that you're going from a higher voltage to lower voltage. Like a system on the DC side is designed for around 600 volts. Coming out of the inverter, you're on the AC side, and it's sized for around 240 volts at the residential level. But then when you get into, particularly for higher commercial electric services, like a 480 volt three-phase commercial electric service, you know, you have a volt times an amp equals a watt. But when you get into three-phase electrical services, you have to use the Pythagorean theorem to get your effective power, and basically you can go from a 600 volt DC system to a 480 volt commercial three-phase system, and it might be that the amperage on the DC side is a little bit higher than the amperage on the AC side. So normally you're going from a higher voltage to a lower voltage, and that means you're going from a lower amperage to a higher amperage. And so normally the DC grounding electrode conductor sizes are smaller than what you'll do on the AC when you check your amperage, and you'll look up the table to see your minimum required conductor size, provided you're not triggering other rules that say you only need to use number 6 when you're actually measuring out the calculating the size. It's common that the AC side is going to be larger than the DC side. But particularly when you're going into a 480 volt three-phase commercial side, it might be that you're going from 600 volt solar to 480 volts AC. But as far as the amperage goes, you're really kind of going from 2 legs of solar, or even 1 leg of solar, to 3 legs of AC. And so it's actually, you might find that the voltage is dropping and the amperage is dropping, but that's more of a nuance of three-phase power that we really aren't going to get into. So what I would just say is don't always assume that the DC side equipment ground is sized correctly for the AC. You know, what happens is, if you do your calculations for the DC size and then you do your calculations for the AC size, particularly on 480 volt three-phase services, you may find that the DC's required size for the grounding conductor is larger than the AC required size. And you can fail inspection by just not looking at the two and saying, if I don't have a separate DC grounding electrode conductor, so if I'm not taking the DC side and running it directly into my ground rod, but if instead I'm taking the DC side and connecting it to the wires in my internal conduit run that go down to the inverter and then come out the AC side and then go down to my equipment ground through the AC side. So if I am bonding effectively my DC side to my AC side at the inverter, you have to make sure that you check both the DC size and the AC size. And if the DC size is larger, you need to carry that larger size through the AC side. So sometimes, in most circumstances, the AC side is larger than the DC side, and so you never run into code violations where you just do your DC sizing, AC sizing, and use whatever the table is telling you to use. But particularly on higher voltage three-phase commercial services and 600 volt solar arrays, you may find that it's the exception to the rule. And so always check to make sure that if the DC side is larger than the AC side and you're carrying the grounding through the inverter, you want to use the larger DC required size as the AC size. Okay, so now we're going to get into Article 300 wiring methods. For parallel wiring, conductors are permitted to be run in parallel under certain conditions. It doesn't say here, but I think that's number 4 or larger wires. So we'll get to it. Let me erase this ink. There we go. Conductors of AC and DC circuits are permitted to occupy the same equipment or enclosures. All conductors shall have an insulation rating equal to the maximum circuit voltage of any conductor within the same enclosure and raceway. And so you're allowed to have AC circuits and DC circuits in the same enclosure, but you have to check your voltage requirements. Remember that DC or AC services are common at 240 volts, 120 volts, maybe 480 volts. And that might mean the jacket of that cable is not rated for the same 600 volt rating that solar could go all the way up to. So you got to check your jacket rating voltage requirements when you're sharing the same thing. And then we also saw that requirement where feeder conductors cannot occupy the same conduit as load conductors. And so we have this informational note that says solar array conductors have to be excluded from non-solar conductors. That information note will probably change in the future. It'll probably say that, you know, on-site distributed power system conductors must be excluded from your load conductors, or just removed from code as people become more familiar with other sections of it. Where subject to physical damage, conductors, raceways, and cables should be protected. So sometimes you can, under some circumstances, you can run through bored holes through your wood members, and that would be considered protected. Non-metallic through metal framing may require some additional protection. Where all these protection requirements come from is that, you know, if you're using a robust fastener to attach, you know, what's called cladding. Cladding would be like drywall clads your interior metal frames. Well, really, it's your surface board up on your roof clads over the framing members. And if you have iron framing members and a metal roof, your fastener that attaches the two is going to be a lot stronger than a typical nail that would attach, you know, plywood to pine wood. And so when you have metal framing members, you're probably using a stronger fastener, and it might require additional protection because they don't want a roofer coming through and putting a fastener through the roof and having it nick your electrical wiring that's underneath the rooftop. So in solar in particular, we have cables or raceways or boxes installed underneath the rooftop. It might be that your rapid shutdown combiner box, instead of locating it underneath the array, it has to be within a 1-foot perimeter. You might want to go into the attic and mount the box inside the attic. And that's going to be a little difficult to do because the roof is sloped, so you'll have to build a little frame so that you can mount the rapid shutdown box upright. And you only have a 1 foot per code. You only have a 1 foot distance to do this. Although I imagine most inspectors are going to be very lenient on that if you're just going directly downward into the attic and wanting to make the box more user friendly. I bet they would. Your local AHJ, you'd want to ask them ahead of time, but would give you a couple more feet to go down for an accessible rapid shutdown box. And that's something we thought about in our design for our solar array because we're buying charge controllers for this DC coupled battery system. And the question is, well, could we just mount our charge controllers in the attic and have our charge controllers rapid shutdown functionality constitute the rapid shutdown requirement for our system? And so you're allowed to go into the attic, and you're going to have a lot of electrical lines running right underneath the roof deck. And so for that, if you're running metal electrical conduit right underneath the roof deck, even if you don't see something like spelled out in code, obviously code thinks about how to protect electrical wirings from fasteners. And there might be some flexibility there where if you have to run your wires directly underneath the roof decking, you may just need to protect them in a stronger metal raceway, or put some metal plating around your non-metallic conduit to protect it. And this is stuff where, if you want to do a building integrated solar design and think about your material selection, you could incorporate metal framing so that you have a rigid metal raceway for your solar conductors to run through in a protected manner, using the framing of the building itself, pathways in the framing itself for your wireways. If you're going underneath the roof decking, you need to have at least 1.5 inches of clearance underneath the roof decking. So hopefully these roofers are smart enough not to be using 4-inch nails when only a 1-inch nail is needed, that they're not going to just be putting metal dangerous spikes into the underside of your rooftop. But you have to have a 1.5-inch clearance between underneath the roof deck, and you also cannot conceal the wires in your metal corrugation. So sometimes in your metal corrugation, you get a rolled form that looks like that, and you might think, oh, can I shove a conduit underneath here and conceal the wires? You're not allowed to conceal wires in a metal corrugated rooftop. Insulated fittings shall be protected smoothly rounded insulating surface unless the conductors are separated from the fitting or raceway by a identified insulating material that is secured and fastened in place. So this applies to number 4 AWG or higher. Let's say you have a 4-inch conduit and you want to shove a bunch of wires into it. You need to have a bushing around that smooths the edges, and you also may need a spacer to space the wires out towards each other. So you may get a spacer inside that fitting as well. Not a bad idea to use on wires that are smaller than number 4. You don't want a rough surface on your conduit eating into your conduit cable anyway. We have a requirement for expansion and deflection fittings on where your solar array may be intended to expand over long distances, and if you're not putting expansion fittings into your conduit can rip apart and start eating into your wires. Not that you can't pull your wires apart either, but you're reducing the safety risk by using expansion fittings substantially. There are requirements for direct burial wires on or wires that are going into rigid conduit, or using other raceways or lower voltage circuits on the sufficient amount of depth or coverage, where if you're digging a trench and you're using direct burial wiring, I think this might have to be, that's 2 feet deep or 4 inches when buried in concrete. And so there's certain required depths that you have to go down to. If you want to run wires underneath a driveway, for instance, you have to have a deeper trench. If you're outdoors and you're protecting your wires and conduit, it's still considered to be a wet location. The conduit in a direct burial wire run it's mainly there for protection. It's not there to put in a pathway that you can just use over and over again if you ever want to add new circuits or upsize your wires in the future. Generally, you put in empty conduits for future expansion if that's something that you want to do. Now, if you're doing a true direct burial wire run, so we do direct burial wire runs in Mississippi where we don't get rock and boulder in our dirt. You're either in good planting dirt that's incredibly sandy and clayey, or you're in a rock concrete, completely uniform shelf. You know, we're not a very interesting geography, I'd say. And so if you're doing a trench, you may just throw your direct burial wire directly into the trench. And so the question is, well, if I have direct burial wire going directly into the trench, where does the conduit end and where does it begin? And if you have direct burial cable emerging from grade, it needs to be protected from physical damage. You know, entering in buildings, it needs to be protected from damage. You know, you need to put a warning ribbon above your service conductors so that when you're digging, you dig up the warning ribbon before you get down to the conductors. So anyone operating a trencher or a backhoe, you know, they know what they're doing. Well, that doesn't mean you don't call before you dig, but if you're burying power lines in the ground, you need to give people a warning label. Otherwise, who knows what's going to happen down the roads in terms of your liability if you're not following code. Now, this is kind of interesting. In direct burial, you can be spliced or tapped without the use of splice boxes. So this is where you can find splice kits that are designed to be outside of a junction box, but that's because it's designed to be inside a direct burial wire run. That doesn't mean that you can take the same splice kit and take it up on the rooftop where it's going to be not buried by ground, but you know, exposed to metal parts. You can't just do a splice outside of a box under all circumstances, but you can in a direct burial. You know, you need to protect the burial cables from earth movement. And so you may need to give yourself some slack in your cable when you come up from the earth. I'm using S-loops to transition in raceways, expansion fittings. So you're using these drip loops not just to get water off the wire, but also to give it some flexibility so you don't pull your wire apart with seasonal changes. Ferrous metal equipment shall be suitably protected against corrosion on the inside and out. So there's a requirement here for our metal boxes to be painted or galvanized, you know, covered in a insulating material to resist corrosion. And that means we can't just butt metal up on metal and assume that it's going to be continuous, because the same way you protect against corrosion, you reduce your electrical conductivity as well. Non-metallic equipment must be listed for exposure to sunlight. Now, you get a different electrician's conduit than you do for a plumber's PVC conduit. Now, plumbing, you know, that's where the sun don't shine. You don't need to worry about plumbing conduit exposed to sunlight. You know, electricians would. But then again, there's other corrosive environments beyond, I don't know, a chicken farm. You know, a swimming pool may be a corrosive environment. You seal your raceways whenever you go, when you pass from the interior to the exterior of the building. The expansion fittings were necessary to compensate for thermal expansion. And so, if your solar arrays become sufficiently long, I think it's something like 120 feet or longer, that rail is going to be giving you some rather substantial expansion and contraction up on the rooftop. You need to use expansion fittings on your conduit so that you don't pull your fittings out of your box. Let's see, some of this stuff is kind of obvious, so we're just going to keep moving through. Conductors and raceways shall be continuous between outlets, boxes, and devices, and so forth. There should be no splice or tap within a raceway unless, and there's certain exceptions, and one exception is you're permitted to do splicing provided that you're not filling up the wireway by more than 75% of its area. It also might has to be a fitting like that's listed, and so again, you might find outside of the box splice kit, but it's only listed for direct burial. It's not listed for all other environmental conditions. And so there are certain exceptions where you can do splicing outside of a box, but generally that's the exception to the rule, not the standard to the rule. When you're doing splices on a solar array, you really need to be putting it inside of a box. Those MC4 connectors are a housing for that splice connection. It's also listed for that purpose. So length of free conductors at outlets, junctions, and switch points. At least 6 inches shall be left inside those switches so that you can, access it and work inside. When the opening is less than 8 inches in any dimension, each conductor shall be able to be extended at least 3 inches outside the opening. I don't see any requirements in the solar industry at this point requiring certain a certain amount of slack in your cables, and it's a fine line between having some additional room in your cable flexibility versus installing the cables in a workman-like area. Generally, you don't want a lot of slack because the conduit box gets messy. So I don't see any similar requirements where you're installing a ceiling fan or maybe a light switch. You have to leave slack so that you can pull the wires out and work inside them. I don't see any similar requirements like that in solar boxes at this time. So if you're using auxiliary gutters, you don't need to put a box inside of that. Then we get into physical protection. And what I want to point out, there is a cable type called MI, and then there's MC as well, where you buy super expensive cable, but it has a lot, some of that expense is in making the cable more robust. And so by buying a cable that is metal clad, you might fulfill a requirement for DC cable being inside a metal enclosure. And it's there so that that cable is becoming more robust. So it doesn't really matter if you put it in EMT conduit or a more robust cable. The point of code at that point is not anything to do with system grounding. It's just trying to give the cables more physical protection. So particularly for interior wire run retrofitting, where you have to drop a solar cable down a wall, You know, you think, well, how am I going to retrofit conduit and put conduit retrofitted down a wall? You know, it might be that you go for a higher end, you know, $5 a foot cable, but you're also saving some money on, you know, now you've turned what would be an impossible job into a possible job, which is the most important. But B, you know, you're also not buying the EMT conduit and all the fittings you necessarily need. So there is some cost savings there that makes up for the higher cost of the cable. And there are installers who are big fans of internal wire runs who just use metal clad cable for their inside wiring because it's easier for their work process. So we have a box, conduit body, or terminal fitting should have a separately bushed hole for each conductor, shall be used whenever there's a change in conduit to open wiring. So that's kind of interesting where you're not a conduit body, you know, your amateur installers will just take your conduit and wires and shove as many wires into the conduit as they can. But what we're seeing is there actually should be a hole for each conductor going in there. And that's where you see these you know, caps that go into your conduit that can support and separate each different conductor. A bushing shall be permitted in lieu of a box where the conductors emerge from a raceway and terminate at equipment such as open switchboards or similar equipment. So, you know, there are exceptions to the rules. The number and sizing of conductors in a raceway shall not be more than what will permit the dissipation of heat and be able to install or withdraw a conductor without damaging other conductors or their insulation. You know, that might be wishful thinking. Usually when you're pulling a conductor out of a cable, you can, but it can also get stuck and hung up on the other cables inside. So often you have to pull everything out and put everything back in. And that assumes your conduit remains intact, as it might not in a direct burial run when you have the weight of the earth pressing down on it. Raceways other than busways or exposed raceways having removable covers shall be installed in a complete fashion between outlets, junctions, or splice points. Where required for utilization equipment, the raceway shall be permitted to be initially installed without a terminating connection at the equipment. Exceptions, short sections of raceways used to contain conductors or cable assemblies for protection from physical damage shall not be required to be installed completely between outlet, junction, splicing, and service points. So what does all this mean? Well, there's a couple of ways you can use conductors on a site. I'm just going to advance to the next slide to have some space to draw. But, you know, basically what it's saying is if you have your junction box and you have a conductor run from your junction box to your inverter, you know, that needs to be a well made up, fitted, continuous run where you don't have just, you know, the junction box and then exposed cables going into the conductor, and, you know, that part needs to be well made up and fitted. But there may be also cases where, you know, let's say this is your solar array, and then this is a commercial array on a flat roof, so you have another section of your solar array, and you need conductors to go from, you know, point A to point B. You know, you might be using a raceway or a piece of PVC conduit simply to, you know, because you have a walkway here, you know, it's much safer to bundle up all this conduit together, and this may only be a 30-inch section of conduit that gets hidden underneath a stairwell or a step, you know. So, but that's not connected in a complete fashion to this solar array or that solar array. And the same way, this is a start to finish completion of your conduit fittings or conduit runs. So you're allowed with short sections of raceways, really only used for protection from physical damage, and not really used to connect multiple pieces of equipment together. Those short sections are not required to be installed in a complete manner. That still doesn't mean that it's not a good idea to go and put, smooth edged bushings at the edge of those, or to even consider spacing the conduits out to better promote heat dissipation. That doesn't mean that even though you might be able to exceed a 40% conduit fill, that doesn't mean that you should exceed a 40% conduit fill, because of heat dissipation. You might be able to cram more wires in there because it's a straight through run. You're not going around any bends, and the wires are laying down compact. That doesn't mean you should cram as many wires into those conduits as you possibly can. Double your conduit supports and use an extra layer of conduit and get better heat, airflow through those conduits for heat dissipation. Support methods for raceways, not only for vertical runs across a roof, but when you're running wires up and down a building, there are distance requirements for just the weight of the wire itself can get so heavy that the wire should not be supporting itself. So you want to bolt it to the side of the building and give it a little bit of load relief. But we're talking about spacing that is like 80 and 100 feet. So you only really get into the spacing requirements when you're building, 3-story tall buildings, 4-story tall buildings, or wind turbines or something like that. Well, when we were building our internal pathway, one thing you would think of, well, could our wires be heating up that metal through ferrous induction? It's more of an AC thing than a DC thing. So there are spacing requirements on conductors going through metal, and your knockouts that are pre-stamped into your metal should be sufficient for that. Openings around electrical penetrations into or through fire-resistant rated walls, partitions, floors, or ceilings shall be fire stopped using approved methods to maintain the fire resistance rating. So if you're penetrating through a firewall, you may need to use additional sealant at that point of penetration with a higher fire rating, so that you don't void the fire rating of the wall. So now we start getting into conductor sizing differences, and there's a wide variety of conductor labels, but there are some patterns that kind of emerge. So here we have conductors for dry and damp locations versus conductors for wet locations. And what we see is wet locations is RHW, RHW2, THW, THW2. Wet locations have this W on them. And what gets confusing is you see this THHN, THW, THW2. This is like a cross-listed cable for both wet and dry locations. So, the letters do have some correlation. Like this -2 is for more harsh environmental conditions. So when you're doing a solar cable, you really want to be using this W, be looking for this W-2, and usually that indicates a good solar cable. What the cables actually are, there's charts in section 300 and 310 that line them out to you. So there's cables listed for sunlight resistance, for corrosive conditions, You're only allowed to parallel cable that, so it's one size is 1/0 and larger. In parallel raceways, the main requirement when you're doing parallel wire runs is parallel raceways need to have identical characteristics. And so if you're trying to take a raceway that has what would call for a 250 kcmil conductor, and you say, well, I want to do parallel wire runs so I can go down into a 4/0 cable size, and I want to do 2 parallel runs of 4/0 instead of 1 run of 250. That's fine, but they have to have parallel characteristics, and that means they have to have the same conductors. Your grounding conductor has to go through them. Your neutral conductors have to go through them, and they have to be the same size as well. You know, they have to be identical. So then we get into tables for sizing your conductors, and the tables are used in lieu of engineering. So you say, well, how are all these electricians who aren't electrical engineers going in around and designing electrical systems of buildings? You know, shouldn't an electrical engineer do that? You know, we have the same thing in the solar industry. How are all these solar guys going and putting solar arrays on rooftops and skipping over the structural engineering aspect? And I think that that's a little bit more dangerous because the building codes are not as well organized as the electric code. But what we have in NEC are tables that are basically fudge factors that allow electrician to spec out wire sizing in a safe manner that mirrors closely the results of your engineering data, but you're allowed to not use the tables and instead calculate your wire sizings off of engineered calculations when you're using a professional engineer to perform those calculations and stamp them. And so you might get some better constraints, particularly with your temperature conditions, because whereas the solar installer designing by the chart, you know, they have to use the harshest applicable assumptions. You know, your engineer might be able to say, well, actually, you know, the true voltage of the system is not going to exceed this much, so you don't need to use this wire. That's over engineering. Then again, you know, there's value in over engineering solar. You know, unlike when you over engineer your building's lighting system and you use a cable that is thicker than you should have, and so, you know, the light is going to work either way. But now that we're talking about energy efficiency, you know, you're going to lose less electricity the thicker your cables are. So if you do over engineers by a size or two, the penalty is you might have a more cost-effective system. You know, there is a point of diminishing returns, but generally you're going to get cut off by physical constraints of upsizing as you get into those levels of diminishing returns. So ampacity adjustments, including temperature correction, are applied to the conductor using the temperature rating of the conductor if the adjusted ampacity does not exceed the ampacity for the temperature rating of the termination. And so if your conductor is 90C, you can do a 90C calculation, but if the terminal is rated for 75C, you may have to redo your calculations at 75C. If the adjusted ampacity does not exceed the ampacity for the temperature rating at the termination. So you need to do a ampacity and temperature calculation at the terminal to make sure that your 75C terminal is not exceeding its temperature rating. And then you can do your calculations for your conductors, 90C conductors at 90C. But you also have to go in and do a separate calculation at your terminal to make sure you're not elevating the temperature of your terminal, which is usually a 75C connection, just because of the way things are listed in the US per UL. You know, they've never really stressed so much of a 90C connection. There's not too many uses for a 90C connection, except now there are, since we're using our rooftop more. Electrical connections, the temperature rating associated, yeah, so it's just a restatement of the previous slide. So when we look at a 30C, 86 degree Fahrenheit ambient temperature, and we're using 60C, 75C, and 90C wire, you know, all of it is rated. The 60C cable can certainly withstand a 30C ambient environment. You know, as the temperatures begin to climb, you know, the cable has to be substantially derated and essentially carry less electricity than it could at lower temperatures, so that the combined effect of that internal temperature of the wire does not heat up to the point where it causes a fire by getting too hot, not because it's arcing electricity into the building or structure. It's just heating up, and that heat is starting a fire. Then we have a same the next table, and it's the exact same chart, but the only difference is it's done at 104 degrees ambient instead of 86 degrees ambient. And so instead of having you know, if you're in this 100, you're trying to correct it for your actual ambient. So now we're a little bit above it, and we have to derate the ampacity by 50%. Whereas if we were doing our calculation based off a lower ambient wire, we would be derating it by 40%. You know, the important thing is that you're being consistent with your ambient temperature. You know, if I'm designing for an 86 degree ambient temperature, these are, you know, that's different versus 104 degrees temperature. It's we're already factoring in additional temperature into the front side of the calculation, and so you get a little bit more leniency on the correction factor. And all that's saying is in a cooler environment, you get a larger, you don't have to discount your wires by as much as if you're in a hotter environment. But if you're doing your calculations starting out at 104 degrees, you know, you go from 104 to 123, you discount by 50%. You go from 86 up to 123 to 131, you have to discount by 40%. And so what you might say, well, what's the difference is? Well, actually, when you're calculating the internal temperature of that wire, you have to look at your ambient temperature, the amount of amperage that's going through it. An engineer would come in and make a more exact calculation, whereas the tables are saying this is for an environment that's going all the way up to 86 degrees ambient. This is for an environment that's going all the way up to 104 degrees ambient. And so it's being conservative on your wire sizing for that electrician who is not actually performing the actual temperature calculation. And so here's our actual temperature calculation where that an engineer could use. You know, and generally we're splitting hairs, you know, by the time that we're deciding between 2-aught and 3-aught, you know, between the smaller wire and the larger wire. At this point in design, more than likely you're going to go with the larger wire anyway because of voltage drop, and then you might have to make a decision between that larger wire and the next larger wire, at which point it's not really an amperage decision anyway. It's more of a voltage drop consideration. You know, usually when you design by amperage, you're going to get to the minimum allowable wire, and then you upsize from there to accommodate voltage drop. You know, can my wire safely carry all the current that's going to be pushed through it, and then can I do that more efficiently by upsizing? Now, if I have one wire and a conduit, it's emitting heat. If I have two wires in a conduit, it's going to have less space inside that conduit. If I have three wires inside that conduit, there's going to be even less space in that conduit, and different wires with different loads on them producing heat at different times. You know, maybe some of the loads are continuous, maybe other loads aren't. But the net effect of putting multiple wires into the same conduit is that inside of that conduit is going to be hotter. And so we have to apply additional discount factors if we're putting more than one conduit wire in the same conduit. And so there are adjustment factors that are applicable if you have more than 3 current carrying conductors in a conduit, which would indicate multiple circuits rather than just one circuit. You know, if you're not maintaining the spacing within those conductors, if the wires are getting tangled rather than being spaced out, if your conductors are being exposed to heightened temperatures such as sunlight on a rooftop, if those conductors are, you know, they're exposed in free air, but there's a difference between a wire hanging in free air and a wire hanging in free air directly above a rooftop. You know, it's one is cooling your wire, the other is barbecuing your wire. And so if your wire is getting down to being within an inch of the rooftop space, you have to add 60 degrees to your outdoor temperature in order to determine your amperage. And so the way that this chart would work is you might be doing your calculations based on 104 degree ambient temperature for getting your ampacity ratings, and you'd be going and looking at all these charts in code that are applicable to 104 degree ambient ratings, but you say, well, wait a minute, you know, up on my rooftop, it's not 104 degrees. Let me clear out this wiring here. Now, up on my rooftop, it's not 104 degrees. You know, I go to PV watts in the summer day, the hourly data, and I see when it's 104 degrees outside, you know, it might be 130 or more up on my rooftop. And then if my cables are dangling within 1 inch of the rooftop, now I have to go and design up in this 176 or maybe even more, you know, see if there's something right here. I might knock myself out of, there might not be any cable out there that's good for my temperature rating. You know, and what that says is in Phoenix, Arizona, where you get into 120 degree ambient days and it can be 190 up on your rooftop, it's a really bad idea to have any kind of wires being within 1 inch of your roof surface. And for that matter, you know, something like this wouldn't work in Phoenix, Arizona, because by the time we're within 1 inch of the roof surface, we're not finding any cables that are large enough to handle the additional temperature rating. But anyway, you know, we go to 104, then we get to our rooftop ambient temperature, and then we add our additional corrective factors, more, you know, in this case, the not more than 3 conductors in a conduit. We might have to, instead of having, you know, if there were 4 cables, you know, 2 circuits of 2 cables each intended to go into these 4 conduits, we might have to double up our conduits and do 8 conduits instead of 4 to get rid of the more than 3 current carrying conductors in a circuit D rating, because we have to accommodate our for that rooftop temperature adder. But the way it would work is if I'm designing off a 104 degree temperature, and then I take and adjust my temperature up to this 168 degree range because of ambient and other temperature corrective factors, then I would have to, you know, it doesn't even give me a 60C or 75C option. It says, look, you're beyond the temperature rating of this cable, so you should not be using it on the rooftop. And, you know, even though you're using a 200 degree rated cable, you need to reduce the ampacity of it by 55% in order to adjust for the fact that the cable is already hot up on the rooftop. And then you'd use a different table that doesn't show the correction factor, but shows the actual amperage rating. And you'd go and make sure that you're using the 140 degree table as opposed to the 86 degree table. So more than 3 conductors in a raceway, exposure to sunlight on the rooftop. Then there's an exception listed. It says if you're using XHHW2 insulated conductors, this raceway may not apply. And so that gets into, okay, we have a couple of different rooftop conductors here. We have USC2, we have PV wire, we have THW2, we have XHHW2. You know, it might be that if we specify a more expensive conductor that is less subject to burning up when it gets into these hotter temperatures, that means we might be able to get around the temperature correction factor by spending a little bit more on our cable. And so those are the gems on why it's worth going through electric code, particularly if you're brand new to any kind of electrical work. You know, it's a lot to learn. When you have more than 3 conductors in a conduit, you discount 20% for 4 to 6, then 50% to 10 to 20, and then by a lot, 65% by more than 41. Your temperature of your conductors is going to vary on if your conductors are enclosed in conduit versus direct burial versus hanging in the free air. And so then we get into other wire sizing tables that are apply to your conductors in a raceway versus in free air. And so we see that this is the 86 degree chart, and we're using 90C wire, and it tells us that, you know, a number 10 can handle all the way up to 40 amps. Then we get into free air, the same wire, number 10, can handle up to 55 amps in free air. You know, it's because it's cooler than if it's enclosed in a raceway. And then we get into charts that are exactly the same as what we just saw, but instead of being done at 86 degrees Fahrenheit, they're being done at 104 degrees Fahrenheit. Remember, all these charts are because you're not actually calculating anything. You're just matching up the values on the charts because you're not an electrical engineer in this circumstance. And so, you know, if I want to calculate my temperature correction factors, you know, I either do that at 86 and then adjust, or I do that at 104 and the harsher elevated temperature is already being considered, because when I go and I look up the differences between my, you know, let's say 86 degrees in a raceway versus 104 degrees in a raceway, we look at number 10, and then we're getting into higher temperature rated conductors here, where we're in a raceway at a hotter temperature, and this number 10 needs a 150C rating to carry 55 amps. Whereas before, in a raceway, you know, we see that this 90C rating is not sufficient to carry 55 amps, so we'd have to go up to number 8. So when you see these tables and in the description, it's like this is 86 degrees, but then you have to go and apply temperature correction factors. So like here we're seeing it's a 104 degree table, but then it's asking us to pick out our actual ambient. This 104 degrees is just for matching up with not table 31015 B2B, but then when you go and pick to say, well, do I need to read table 31015 B16 or B16 for free air, or do I go to B18 for in a raceway, or B19 for in free air? You know, you match up your temperature condition, you match up your environmental case, and then you read the chart to see, okay, well, number 10, I can have all the way up to 73 amps. Then I have to go and apply my temperature correction factor from the previous chart to say, well, if I'm actually at 40 amps, and I apply a 50% temperature corrective factor because I have 10 of these in a conduit, you know, then I don't have 73 amps of capacity. I only have 35 amps of capacity. You know, and then I have to apply my another temperature corrective factor that might be, you know, as much as, you know, up to, because we're boosting, because we're within an inch of our roof, up to 45%. So all of a sudden, what a cable that's rated for 70 amps, because there's more than 3 in the raceway, gets knocked down to 35 amps. And then because of ambient rooftop temperatures, it gets knocked down another 45%. So now we go down to about 15 amps. And then we have to adjust by the 25% for the non-continuous load, or for the continuous load. That goes down to from 15 amps down to about 12 amps. And then you go from a non-continuous load to also that the STC rating is messed up. So on DC, you have an additional 25%. That gets it down to 8 amps. And so all of a sudden, we have this big, thick number 10 cable with a robust jacket that could handle, if it were inside the house, all the way up to 55, all the way up to perhaps even, you know, this, in this case, we use this very robust jacket. This number 10 cable can handle up to 73 amps in a raceway, but then you put it on the rooftop with a whole bunch of other conductors in a DC application, and all of a sudden up on the roof, it can only hold 8 amps. It just so happens that a lot of solar equipment is designed to accommodate up to a number 10 cable, and solar modules are outputting around 8 amps. And so often up on the rooftop, for a variety of reasons, you're using number 10 cable on the roof for your solar module to solar module connections. So anyway, we're approaching the end of our course, and we're really only scratching the surface of Article 310. You know, I don't want to rush through it, but then again, we didn't really accomplish our goal of getting all the way through National Electric Code. So you've gotten the contact hours, and we've spent a lot of time on the fundamental basis of oddball rules that reflect later in code, but we didn't cover all of the course content. This is only our second time teaching it, and maybe we need to expand the hours of the program. But if you want to take the rest of the course kind of on your own time, just send me an email. I'm always happy to make video recordings and audio recordings available for Halfman customers. And this course, this code course, is our newest program, so we have to update it a few times before we really fall into our rhythm. So anyway, you have my email address. It's jrskromer@gmail.com. Just kind of to fast forward some other parts. You know, we saw yesterday how you could go to use Solar Design Tool to run a National Electric Code report that focuses on Section 690. So if you want a little bit more solar specific content, I encourage you to go to Solar Design Tool and sign up for a free trial, run a design. You know, if you have questions, I can help you with that. If we had more time, we would go in and talk about the different kinds of code, cable and their material. You know, see what your you're missing out on all this lively discussion. We talk about how not just conduit, but boxes and junction boxes have minimal sizing. So generally you size to be no more than a 40% conduit fill. And you actually have less conduit fill for 2 wires than 3 or 4 just because of how they tangle up. But boxes are the same way. You design the boxes to be no more where the conductors inside them, just like conduit, can't be at that 40% fill. But you also have other stuff occurring inside a box, and that other stuff cannot exceed more than 75% of the junction box cross section. So in my designs that I get on my line side tap connectors, I look at my conductors going into a supply side tap, and I think, well, you know, if I have 4 2-inch conduits, that could go into a 12-inch box. But it may be that the conductors in the box, the fittings, can only accommodate no less than 75%. And so if I have 8 inches of conduit going into a 10-inch box, that would be greater than 75%. I'd have to go the next step up. So sometimes you can accidentally undersize your boxes because you're just plugging in a lot of stuff into that box, and it might. So that's something to take a look at. Let's see, some other stuff to take note of before we pass you back to Half Moon. So we get into box sizing discussions, and then we go, you know, here we have the different cable types laid out and better illustrated. You know, MC cable's pretty interesting because DC has to be in metal enclosure, and you already have that metal enclosure in MC cable, and it can be installed parallel to framing members and on the undersides of joists. So you can actually, you know, do some nice internal wire runs with MC cable. You just have to look out for that undersized ground. You know, it might be that you can use this ground for your equipment ground conductor, but you have to run a separate DC grounding electrode conductor up to the roof, independent of this, because it might need to be number, you know, if this is number 10, you know, then often this cable might be number 8. If this, or sorry, this cable might be number 12, and that wouldn't meet the number, the smallest. That would be too small for your smallest equipment ground conductor for a solar array. So you sometimes need to run your grounding separately, and where you do run an equipment ground conductor separate from the rest of your array conductors, it still needs to be run with your wires. Let's see. If I just, yeah, it's common to use USC2 cable up on the rooftop as solar cable. It's a service entrance conductor, but it's a very robust service entrance conductor. Let's see. One thing not to forget is that with tubing, you know, it has a minimal bending radius. So if you get into larger and larger conduits, you need to leave yourself more space in the control room for bending that wire. And then let's see, then when we get into larger panel boards, we say a panel board shall be protected by an overcurrent protective device that has a rating not greater than that of the panel board. This overcurrent protection device should be located at any point on the supply side of the panel board. So if you have a 200 amp rated service panel, you put a 200 amp main breaker on it, you're no longer getting into that upsizing to the next nearest breaker. You know, your main overcurrent protection device, you know, should protect you from drawing in too much current and not create a safety hazard by allowing you to draw in 250 amps when it's only rated for 200. Fast forwarding into, Section 5 is special occupancies. The only thing to take note of that I think is interesting is there's a section for floating buildings, and floating solar is a really interesting concept where you put solar on, say, a wastewater retention pond, where the wastewater retention pond, the stormwater retention pond, there is a lot of net gain to be had by covering the pond, where you can retain more water because of evaporation. You also grow less algae because you're reflecting the sunlight away from the lake, and you don't want algae in your water collection ponds. It gums things up. So floating solar, it's like free land and the city gains, and if you can sell them the electricity at their cost, then great. You get a free job site and a long-term civic-minded customer. And there is parts of National Electric Code that might not be specific to floating solar, but is specific to floating buildings. Section 600 is special equipment. So you get into battery storage, solar. We showed you yesterday how to generate a National Electric Code report for solar systems. The generating capacity is the big one on your interconnection agreements per code. The generating capacity is the inverter maximum continuous output capacity. I don't want to take up more than your time, than your required time, but as we've said in class, your output circuit currents is a sum of module short circuit currents plus an additional 25%. After section 690, after the solar section, this is where you find rapid shutdown requirements. This is where you're allowed to use USE2 and PV wire for outdoor locations on PV source circuits. You are allowed to run DC circuits inside a building, but they need to be contained in metal raceways. Capitalize your letters on your warning labels. The junction boxes are allowed to be located behind the solar modules on your rooftop. So an inspector might tell you, no, they have to be accessible, so they can't be hidden underneath the array. That's not true. So then we get into beyond section 690, it's called special conditions. And your special conditions are emergency systems, standby systems, and this is also where they're putting in the microgrid aspects of multiple on-site distribution systems. And this is where that 120% rule for load side interconnections is located. That's 705.12D or B. Maybe they've changed it around in this one, but that 120% rule is a special condition when you have both service power and on-site power. And so we see it appear in section 700. As far as batteries go, one thing to keep in mind is batteries are done at a referenced as a nominal voltage. So it's very common to have a 48-volt battery be charged above 48 volts. Maybe a 53-volt or 54-volt state of charge might be charged with a 60-volt charge controller. When your battery bank is more than 5 feet away from the equipment, you'll need not just a disconnect switch at the equipment, but also at the battery bank itself. So it might be a good idea to put in a DC distribution panel to parallel your battery circuits before running back to the inverter. Even if you're going to run back to the battery inverter system with parallel conductors, you still might want to parallel your batteries together at the battery bank. It's probably the best way to do it if the batteries are more than 5 feet apart. I've done a large battery bank. It seems like it makes sense to do a dedicated panel for paralleling multiple lead acid batteries together, even when there's less than a 5 foot distance. 1 inch clearance between the batteries and the wall structures on sides that don't require maintenance. If they do require maintenance, you need your working space, which is 36 inches. Anywhere from 3 feet to 3.5 feet to 4 feet if you're back to back against another piece of electrical equipment. 706 is the energy storage system component, and then we get into microgrids, which is kind of a newer section. And then we get into the nice construction tables on the back for conduit bending and annexes. And that's the end of the program. So we didn't get all the way through. We got close to it. My email address is in the chat box. I'm going to type it in again. You can just email me at jrskromer@gmail.com. This is one of the programs that we constantly update, improve, and do supported course recordings on. So if you want access to the course content material after class, just send me. With that, we're over time, so I'm going to pass it back to Half Moon. Thank you for coming.
Okay, great. Thanks, JR. Thanks, everybody in attendance. This concludes the series. I'll close things down. Everybody will be sent to that brief quiz. If you don't want to take it now, you'll receive it via email in an hour. Everybody will receive that email, so if you've already taken it, you can disregard it. Your certificates will be emailed to you within 5 business days, and after we get a quiz submission from you, too. If you need them any sooner for relicensing purposes, either contact our office or you can reply to any of the emails you received about any of the webinars you've taken, and we can help you there as well. That's all I have. Again, thanks everybody, and here's your quiz.